We will start our analysis with flexure, described in Chapter 22, Section 22.3 of ACI 318-14. Our section is a doubly reinforced concrete beam, with the bottom steel labeled number 1 and the top steel labeled number 2 in the diagram. In reality, the steel will contribute capacity both in tension and compression. However, we will analyze this section as a singly reinforced concrete beam in two different scenarios. First, if the beam is simply supported and no moment is transferred at the connection between the anchor and the ramp wall supports. And second, if the beam is fixed and there is moment transfer at the anchor ramp wall connection. In the simply supported case, we have compression at the top of the beam and tension at the bottom, with a maximum moment of WL squared over 8, which is resisted entirely by the bottom steel, number 1. In the fixed case, we have tension at the top and compression at the bottom at the point of maximum moment, with a maximum moment of WL squared over 12, which is resisted by the top steel, or number 2. And you can see that that moment is actually at the supports and it's going to be negative, or the opposite direction of the simply supported beam moment. So when we draw and before we draw a view of the section, you can see the simply supported and fixed supports, and I've shown where compression and tension is occurring. And for the fixed support situation, this eventually will flip, as you can see by the moment diagram, but this is just at the point of maximum moment. So when we draw a view of the section, the acting forces are going to be the tension from the steel at the bottom and the compression in the concrete at the top. This force couple is what balances the applied moment, which comes from the flexural stress, or creates the flexural stress in the beam. So we'll have a diagram of our strain, which complements the diagram of our forces, and is directly proportional to stress. And the point of zero strain is going to be our neutral axis. The depth of the concrete block that is in compression, labeled CC and A here, is the Whitney stress block. So in this equation, for A, the variables are as follows. We have AS1, our steel area, our tension steel area, Fy, our steel yield stress, F'C, our concrete compressive strength, and B, our section width, which I'll leave everything in US customary units, and we can come back to metric at the end. So for our example with the A2 anchor, we have number 6 bars at 0.44 square inches, 40 KSI strength rebar, 1.5 KSI concrete, and a W effective of approximately 42.8 inches that we can read off of our drawing set to give us a value of 1.94 inches. And then we can get clever and define point A at the centroid of the concrete compression reaction. So I've drawn that in green here. And the sum of the moments about point A will be our nominal moment capacity of the section, which is equal to Ts times D minus A over 2, where Ts is the tensile force in the steel, which at yield is just our steel area times our steel yield stress. And for our example anchor, Mn is then equal to our number 6 bars area multiplied by our 40 KSI multiplied by our lever arm of D minus A over 2. And D is the distance from the compression side of the beam down to the centroid of the tension steel, and that can be found in the anchor detail dimensions. This gives us an answer of about 2,500 kip inches, or 286 kilonewton meters of nominal moment capacity.